The purpose of today's video is to preview the final model in our progression of the atomic structure. And the final model that we're going to be looking at is our quantum mechanical model. It's also sometimes called the electron cloud model. Now, based on your reading and based on your guided reading assignments, I'm hoping that you have a little bit of knowledge regarding how this model came to be, but we are going to do just a quick either preview or review with you. When we were looking at our quantum mechanical model, we're kind of turning the idea of wave-particle duality on its head. When we looked at Bohr's model, we talked about how photons of light were given off by electrons as they jumped between energy levels. And these photons of light were really thought of as particles of light, or particles of a type of energy, which introduced the concept of wave-particle duality because light, which is classically thought of as a wave, can also be thought of as a particle or a photon. When we're talking about our new model, Schrodinger's model, the quantum mechanical model, we're really doing the exact opposite. We're looking at something that is considered a particle, those electrons, and we're considering how they can have wave-like behavior, specifically wave-like behavior as they travel around the nucleus. So what Schrödinger and Planck and Heisenberg started looking at is the idea of an electron not traveling just in circular motions, but instead like a wave would travel. And they talked about how the fact that as it traveled around the nucleus, some of these wave functions would continue because the beginning of the wave hits the end of the wave and it just kind of keeps going with its motion. That would be an allowable distance from the nucleus. But then they showed how some of these pathways, when you get to the end, it's not at the same place as the beginning, and therefore that distance would not be allowed. This idea got slightly complicated when you actually add the calculus into the wave functions. However, the general idea kind of stays the same. So the purpose of our quantum mechanical model is no longer to actually be able to draw exact locations for the electrons. Instead, it's to describe the general region where an electron is most likely to be found. And because we're talking in terms of most likely to be found rather than the exact location, sometimes you'll also see our quantum mechanical model called the probability model. It's the most probable region. So in order to describe the region that an electron is most likely to be found, there are a set of quantum numbers. And these quantum numbers are actually the mathematical solutions to our wave function from Schrödinger. Now, we're going to simplify these quantum numbers into four general categories: principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. And I'm going to give you a fairly simple example of an electron cloud model, and then we're going to try to pull each of these out of that model so that you can then preview the vocabulary that we'll need for the entire second section of this unit. So in order to do this, we're going to look at an atom of oxygen. And the first thing we're going to do with oxygen is figure out how many electrons a neutral atom of oxygen has. So we look it up on the periodic table, and we realize that oxygen has an atomic number equal to 8. So we know that that has 8 protons, which means if it's a neutral atom, it also has to have 8 electrons. And now our goal is to describe where each of those 8 electrons are in terms of each of these types of quantum numbers. So if we look at an atom of oxygen, the first 2 electrons in an atom of oxygen are somewhere in a spherical region that's fairly close to the nucleus. One of these electrons spins clockwise and one of them spins counterclockwise. The next 2 are in a slightly larger spherical region, so it's further from the nucleus. But again, it is spherical, and again, there are 2 electrons in there, one spinning clockwise and one spinning counterclockwise. The next 2 electrons in our electron cloud or quantum mechanical model are being described in a figure 8 region. So it's not the complete sphere. Now, the most probable location is going to be confined to somewhere along that figure 8 region. But again, there's 2 electrons in there, and one is spinning clockwise and one is counterclockwise, and that's along the x-axis. The next 1 electron is in the same size and same shape region as the last 2, but this 1 electron is on the y-axis instead of the x-axis. And that electron is actually spinning clockwise, And then the final electron in oxygen is somewhere in that same size and same shaped region as the last ones, but now it's on the z-axis, which would actually be coming out of the whiteboard at you. So again, not that we can see it anymore, but we started with 2 electrons in a spherical region close to the nucleus. Then we made a spherical region that was a little bit further from the nucleus. And then we made 3 sets of figure 8s. The first 2 electrons in a figure 8 were along the x-axis. The next electron that was in a figure 8 was along the y-axis. And the final electron in oxygen is in a figure 8 along the z-axis. And notice all 3 of those figure 8s were the exact same size as the second sphere. This is what the model would look like for our quantum mechanical model of oxygen. And I'm sure you can imagine that if this is what oxygen's electron cloud or quantum mechanical model looks like with just 8 electrons, if you had an element that had 100 electrons, this is going to be a hazy mess. It's really difficult to be able to discern anything out of a pictorial representation of the quantum mechanical model. But we need a different form of this model that still allows us to determine everything about the regions that I just described. So what we're going to do right now is we're going to talk about something called an orbital notation. And this is actually what we'll spend the second half of the unit on really mastering. But for today, we're just previewing it so that really we can look at the vocabulary terms you need. So for our probability model, the quantum mechanical model, the electron cloud model, whichever of the 3 you want to call it, we can better represent the ideas in the model using an orbital notation that looks like this. So we have a set of numbers, 1, 2. We have a set of letters, S's and P's. We have lines above each of those number letter combinations, and then above the lines we have these arrows. And to a scientist, this orbital notation represents the exact same thing as this picture, but in a much clearer way, and both of these things represent all 4 properties of the regions and the electrons that must be described in order to completely really describe the quantum mechanical model. So let's start again with our picture. And let's tie the picture into the orbital notation that we have drawn here. And as we do that, we'll describe what each of these things is actually telling us. So the first thing I'm going to draw in, even though you won't be able to see it for long, is my nucleus. I still have the nucleus in the center of the model. The next thing I'm going to draw in was the first region that we described. And the first region we said was a small sphere that was close to the nucleus. So if we think about the first type of region that we're representing in our orbital notation, which sometimes instead of just a line, it's an actual box. Sometimes the box goes around the whole thing. Either way is fine. The first thing that we described is the fact that it was small, and then we said it was a sphere. And those 2 things are 2 of the properties you need to describe for the region. So the principal quantum number tells us the size of the region. We said it's close to the nucleus, it's small. The angular momentum quantum number tells us the shape. The shape of the region we said was a sphere. You have to include the size and the shape of the region in each of these areas for the quantum mechanical model. The way we do that is actually this number-letter combination. And in order to figure out which is which, let's think about the second region we described, because we said the second 2 electrons were also in a sphere, but it was a larger sphere. So compare this region to this region. Look at the number, look at the letter. What's the same, what's different? Which part of this needs to tell us the size, and which part of this needs to tell us the shape? Well, since the numbers are different and the sizes are different, that means that the size has to be described by a number. The number tells us the size, and really we just say n equals 1 to 7. where number 1 is small, number 7 is big. And if the number is telling us the size, then the thing that was the same, the S in both of these, well, that tells us the shape. Both of them were spheres. So letters equal shape, and you'll see L equals, and it would either be an S, a P, a D, or an F. Sphere, figure 8, four-leaf clover, flower. And we'll get through all of that within the next part of the unit. Once you have described the size and the shape, the next thing that we generally have to describe is the magnetic quantum number. But I didn't do it for these first two because the truth of the matter is a sphere doesn't actually have distinguishable regions that would be described by a magnetic quantum number. You might notice that there's only one line above these S's. And that's because the magnetic quantum number actually describes the orientation of the region around the X, Y, and Z axis. And when I started describing that, it was with a shape that would actually look different depending on whether it was on the X, Y, or Z. Because a sphere is really on the X, Y, and Z simultaneously, there's only one orientation for a sphere. But when we move to those figure eights being the P, that were the same size as the second sphere, because the number is again a 2, now we have 1, 2, 3 lines, because that can be on the X, the Y, or coming out of the whiteboard at you, the Z axis. X, Y, Z. The magnetic quantum number tells us the orientation, and oftentimes you'll see M sub L for magnetic quantum number, and I'm just going to write that these represent the lines. The final thing that we need to include in our quantum mechanical model is then the spin. And the spin is actually not going to be for the region, it's for the individual electron within the region. So if you can picture, let's say that this is my electron. My electron within each of these regions could be spinning either clockwise on its own axis or counterclockwise on its own axis. So again, it could be anywhere within each of these regions, but as it's in the region, it's either spinning clockwise or counterclockwise. And notice, when I changed that, I did not actually change the direction that it's spinning around the nucleus. I just changed the direction that it's spinning around its own center. That's going to be determined by the spin quantum number. And if you think about our orbital notation, the only thing we haven't already described were these arrows. The arrows represent the electrons, and the direction of the arrows tells us the spin. So M sub S is the spin quantum number, and that's just going to say whether it's an up or a down, which would be clockwise versus counterclockwise. These four properties need to be described in order for the orbital notation to represent the quantum mechanical model. And what you're going to be doing within the next part of the unit is really being able to describe how each of those things happens. You'll also learn how to actually draw out these orbital notations. So again, this is a quick lesson. You don't need to know a whole lot about the quantum mechanical or electron cloud model for tomorrow, but you definitely want to remember that the big difference are that this is a probability model, which really just means here we were identifying where the electrons were at, right there. And with the new model, we're just saying, hey, they're somewhere within each of these regions. We're not saying where within, just that it's somewhere in there. You also need to know that this new model, Schrodinger's quantum mechanical model, is going to have more than just circle-shaped regions. Now we have spheres, figure eights, four-leaf clovers, and flowers too, but we'll get to the more complex ones after the quiz. If you have any questions about the material from the guided reading, if you have any questions about any of the material from the flame test preview work, really anything from any of the modules that we've done the past couple days, absolutely let me know. Other than that, your quiz will be tomorrow, and it will cover all of our different atomic models.